Alright, so here is our first lesson of second semester. We're going to be working on indefinite integration. So follow along and pause the video as needed so that you guys can copy notes down or go back and rewatch it as needed to understand the material better. So integration is essentially the opposite of taking derivatives. They are inverse functions. Similarly to the opposite of addition being subtraction, the opposite of multiplication being division, etc., etc. The opposite of a derivative is an antiderivative or integration. So we're essentially undoing derivatives in second semester when we're talking about integration. When you take a derivative and then you take an integral, you should end up exactly where you started, with the exception of a constant of integration, and we'll talk more about that. So, like I said, these are called inverses. We can call it anti-differentiation, but we can also call it integration, and integration is typically more often the word that you guys will hear me saying, or the word integral, taking an integral of something, but essentially they mean the same thing. The antiderivative and the integral are the same thing. It says, for instance, we know that the derivative of x cubed is 3x squared, so it makes sense to say that an antiderivative of 3x squared is x cubed, so it should undo it. Notice that it was the word the, and they crossed off the word the and put the word an. The reason there is because of this constant of integration that I was mentioning earlier. Because if we add on a constant to the end of x cubed, like x cubed plus 3, if we would have taken the derivative of that, it also gives us 3x squared. So as long as you're adding a constant to a function, when you take its derivative, the constant will go away. Therefore, when we take the antiderivative, we have to account for that, the fact that there could have been a constant there before. And like I said, we call that the constant of integration. So again, that's why it's important to talk about an antiderivative rather than the antiderivative. We call this a family of functions. So all of the 3x squared functions plus constants would be, would be families of functions. So you can see that here. It says for x cubed the derivative is 3x squared, but that's also the derivative for x cubed plus 2 and x squared minus 5 and x cubed plus 6 pi, etc., etc. So all of these have the same derivative. Therefore, the antiderivative of 3x squared or the integral of 3x squared will have to account for that, the fact that the constant could be different every single time. So there are an infinite number of functions whose derivative is 3x squared. Therefore, when we take the antiderivative, we add on this plus c. So you guys can see that the antiderivative of 3x squared is x cubed plus c. We call that c a constant of integration. So you might want to write that down in your notes. That plus c is called the constant of integration. And every time we take an antiderivative, it's super important to add that plus c, just so that we know that there was a constant that could have been there. And again, we call it a family of functions rather than one specific function. Move on. There we go. So the process of taking antiderivatives is also called integration or indefinite integration because we are getting expressions, like mathematical expressions, as our answers. We're going to get into later on something called definite integration, which ends up giving us a number. So our answer is numerical instead of algebraic. And I'll explain more when we get there about what the difference is between those two. So because we're just finding a family of functions, it's this constant of integration c that we add. This symbol, it looks like a really long elongated s. This is called the integral symbol. So anytime you see that symbol, it just means to take the antiderivative or to take the integral of that function. And here's how we write it. So we say the integral of some function and dx. Notice here we have dx. That is called oh my gosh, forgetting off the top of my head. But this is essentially leading up to, I forget the important word for it right now, but essentially leading up to the fact of saying that this is the important variable with which we are taking the integral with respect to. Kind of like with derivatives, how we say dy dx. Oh yeah, you can see that right here, it even says it. How we have dy dx. Dx is the important variable that we are taking the derivative with respect to. When we actually take integrals, we multiply that over to the other side, that dx. And so essentially the integral becomes our important variable with x's in it. So f of x plus c, that constant of integration, and then it just essentially is telling you what the important variable is. So this is simply notational. It actually doesn't do anything to the problem other than tell you the important variable. It doesn't affect our answer at all, and you'll see that later on. So here's some more examples and some formulas that it's important to write down in your notes. It says the derivative of 4x is 4, therefore we say that the integral, remember this elongated s symbol is the integral symbol, therefore the integral of 4 dx meaning that x is the important variable here, would be 4x plus c because of that constant of integration. And the derivative of x squared plus 3x minus 1 is 2x plus 3. So notice that when we take the integral of 2x plus 3 going backwards, 2x turns back into an x squared, the 3 turns back into a 3x, and then the constant of integration we add on to the end. Notice that it was a negative 1, but because the derivative kind of eliminates that piece of it, we can't tell exactly what that number was yet. We just have to add this constant of integration c, and we can figure out later on if we're given more information about the original function, we could figure out what that c value was. But for right now, we just have to put a generic c in there to hold the place of that constant. So here we're going to go over some derivative and integration rules that go hand in hand. Make sure you guys write these in your notes. So the derivative of constant is 0, therefore the integral of 0 is a constant. The derivative of some value times x is equal to k, therefore the integral of some constant, k, is equal to kx plus c, because again, it could have been like the derivative of 3x plus 1, and that would have just been 3. We don't know what that constant being added could have been. The derivative of k times some function f of x is k times the derivative of f of x. That's the one where we say that it's a constant being multiplied, a constant multiple, and it just tags along for the ride. So the integral of k times some function f of x is the same thing as pulling that constant out front. You can kind of like pull it outside of the integral and let it tag along for the ride as you take the integral of f of x. And then again, plus c. The derivative of two functions being added together would be the derivatives being added together. And so same thing with the integrals. The integral of two functions that are being added together is the same thing as the integral of each of those functions individually. And last but not least, the reverse power rule. So when we take the power rule, we bring the exponent down front and lower the exponent by 1. So bring the n down front and then subtract 1 from the exponent. The power rule reversed would be if we're taking the integral of something, you up the exponent by 1, so bump up whatever the exponent is plus 1, and then divide by the new exponent. And again, you guys will see that worked out a lot in this video, so hopefully it'll become a little bit clearer. And then the plus c is just the constant of integration again. So let's do some examples. All right, the integral of 7. 7 is a constant. So, let me pull up my little pen here. Seven is a constant. The integral of a constant, and look at it being our important variable is dx. The integral of a constant is 7x plus c. And at the very beginning, when you're just getting used to these, it's easiest to, like when I put an answer up here on the board, it's easiest to understand like how I got that by actually taking its derivative and making sure that you understand the relationship between the derivative and the integral. So for example, if you come here to this function, if you go backwards again and take its derivative, the derivative of 7x is 7, and the derivative of a constant is 0. So the derivative of 7x plus c would just be 7. So notice that again, the integral is undoing the derivative, and so when I undo this derivative, it adds that x back in, and then plus c for my constant of integration. For the second one, this is going to be a reverse power rule. So remember, for the reverse power rule, you bump up the exponent by 1, so that would be 5 plus 1 to be 6, and then you divide by the new exponent. So x to the 6th over 6 plus c. You'll also see this written a lot as 1/6 x to the 6th plus c. So I'll write my answer like that. For the next one, again, a reverse power rule. If you bump up the exponent by 1, you get x to the 13th over 13. I'm just going to write it as 1/13 x to the 13th plus c. Alright? For these ones, they are a mixture of the reverse power rule, along with the fact that we're adding and subtracting functions. So notice that I have two different functions that are being subtracted here. When I take the integral, I just treat it as if they're separate functions and take the integral of each piece individually. So the integral of x to the 4th is x to the 5th over 5, or 1/5 x to the 5th, minus the integral of x squared is x cubed over 3, or 1/3 x cubed, and then plus c, that constant of integration. And again, if I lose you at any point in this process, you can remember, like, wait, how did that work again? Like, why is that the integral? Try to take the derivative of this. So if I bring the 5 down front, notice that 5 times 1/5 is 1, and then if I lower the exponent by 1, that would be 1 x to the 4th, which was here. So the integral is essentially coming to this point where we're undoing that, and then if you want to check it, you can always take the derivative of this function again. The derivative should be equal to what was inside of our integral up here at the beginning. For number 5, go ahead and try to pause the video if you want and do that one on your own, and then pick up with us as we look at it together. So the integral of t cubed is t to the 4th over 4, or in other words, 1/4 t to the 4th. The integral of t is t squared over 2, or 1/2 t squared. The integral of 1 is just t, and then plus c at the very end for that constant of integration. Again, if you need to, check it using derivative rules. It should take you back to what was inside of the integral to begin with. Notice this next one. We have, excuse me, we have a 3 in front of it. So technically the correct mathematical notation would be to rewrite this first before you take the integral. So taking that 3 out of the integral and writing it as the integral of x cubed dx, and the 3 just comes out front. It's not the worst thing in the world, and nobody really cares if you leave the 3 inside, because when you get more familiar with integrals, it's just the quicker way to do it. There's no point in rewriting it really, but just to show you that the 3 gets multiplied times the integral of x cubed, which is x to the 4th over 4, or in other words, 1/4 x to the 4th dx, or sorry, not dx, plus c. So if I multiply that, I just get 3/4 x to the 4th plus c. And again, to check it, to make sure it makes sense in your mind, take the derivative of this. If I take the derivative, I have to bring the 4 down front. So the 4's would simplify to be what? 1, and that would be 3x to the 3rd power. Excuse me, which is what I had originally. Alright, let's keep going. So if you want to try and challenge yourself a little bit, try to do some of these on your own. And then kind of pick up where we left off in this video, and then check your answers as we go through them together. For number 7, we are subtracting 3 functions together, so let's take all of their integrals individually. Now, I'm not going to pull out the numbers and show them being separated. I'm just going to show you guys all in one step, so bear with me as we do that. The 2 in this first part right here is just a constant multiple, so remember it just tags along for the ride with derivatives, but it also tags along for the ride as an integral, so it just stays out front. Then the x squared, the integral of x squared is, I'm going to start writing these as fractions. Instead of coefficients as fractions, I'll write them as fractions individually. Since we have a coefficient already, we'll kind of use that as we go. So the integral of x squared is x cubed over 3. Again, we could write that as 1/3 x cubed, but because we have this 2 in front, I'll just write it like that. And then if it simplifies, great. If not, we'll just leave it like that. For the next one, we have 7x. So the integral of x is x squared over 2. And the integral of 8 is negative 8x plus c for our constant of integration. Now, it just so happens that none of this really simplifies. You might see it written like that. You might see it written as 2/3 x cubed minus 7/2 x squared minus 8x plus c. So I'll write it like that because I think that's typically more often how you would see it. Now, for the next one, again, I'm kind of going back and forth. I hope it doesn't mess with you guys too much. Going back and forth between writing the divided by part as a coefficient that's a fraction and then writing it actually underneath the function. On this one, I like to write it underneath the function because my coefficients that were there to begin with were just whole numbers, like 2 and -7 and -8. So when I divided by my exponents, it kind of created this nice fraction for me. You're going to notice on this one, however, that the coefficients themselves are fractions. So if I write it as like 3/4 divided by the new exponent, it just creates a complex fraction. That's probably not the easiest thing to deal with. So instead, I'm going to actually write these as our coefficients that we already have. And then when we use the antiderivative rules or the integral rules for all of these x values, the reverse power rule, I will write their divided by part as a new coefficient, so you guys can see it that way. That way we just have to multiply fractions rather than dealing with complex fractions. So for example, on this first one, we have 3/4, and then the integral of x to the 5th is x to the 6th over 6, but I'm going to write it as 1/6 x to the 6th. Again, the purpose of me doing that is because now I just have to multiply these two fractions rather than having to work out like putting divided by 6 down here and then working with that complex fraction. So it's probably easier just to do it like this if our coefficients are already fractions. For the next one, we have 5/3, and then the integral of x squared is x cubed over 3, or 1/3 x cubed. And then for negative x over 2, that's technically a -1/2. And the integral of the x is x to the 2nd power over 2, or 1/2 x squared. And then plus c. So if I simplify this, in this first fraction, if I multiply the numerators, I get 3. If I multiply the denominators, I get 24. So 3 over 24 turns into 1 over 8 x to the 6th. If I multiply the numerators, I get 5. If I multiply the denominators, I get 9, and that does not simplify, so plus 5/9 x to the 3rd power. And then if I multiply the numerators here, I get 1. If I multiply the denominators, I get 4, so that's minus 1 over 4 x to the 2nd power plus c. And that is about as simple as we can write that problem. For number 9, the integral of pi x. That pi is a constant, so it tags along for the ride. The integral of x is x to the 2nd power over 2, or 1/2 x to the 2nd power. The integral of 1 over pi, since 1 over pi is just a constant, would be 1 over pi times x plus c. So if I want to simplify this at all, I can write it as pi over 2 x squared plus 1 over pi x plus c. All right. Now, we're getting into ones where we may need to rewrite a little bit because these are all technically the power rule, but because none of them are written as x to an exponent, they have other things happening to them. It's our job to be able to understand what the exponent actually is. So for example, on number 10, I would want you guys to rewrite this as x to the -2 dx. When you rewrite it that way, now you have x to an exponent. So if I bump up the exponent by 1, adding 1 to -2 would bump me up to a -1. So that's x to the -1 over -1 plus c. Now again, for your response, feel free to leave it like that, but on a multiple choice, they would not. So the x to the -1 would go back to the bottom of the fraction, and then the negative could stay down there with it. So it would be 1 over negative x to the +1 plus c. And again, to convince yourself that this is the correct integral, make sure to try to take the derivative of this. See if when you take the derivative, you get what was inside of our integral to begin with. All right, on number 11, if I rewrite these, I have the integral of 4x to the -3 minus 5x to the -4 and then dx for my important variable that I'm taking the integral with respect to. The integral of 4x to the negative 3, let's see. If I bump up the exponent by 1, that would be 4x to the negative 2 divided by negative 2, my new exponent. And then minus 5x to the negative 3 divided by negative 3, my new exponent, plus c. I can simplify this a little bit. On this first one, I have 4 divided by negative 2 would give me a negative 2. And then this x to the negative second power would go back to the bottom of the fraction as x to the positive second power. On this second term, the negative and the negative would make a positive, but 5 and 3 don't simplify, so that would just be plus 5 over 3. And then notice that x to the negative 3, because it's a negative exponent, will move to the bottom as x to the positive 3 plus c. And last but not least, number 12. For the square root of x, I can rewrite that as x to the 1/2 dx. If I bump up that exponent by 1, that becomes x to the 3/2 over 3/2. Now, you guys are going to start to see me doing a shortcut when it comes to problems like these. Oh, don't forget about your plus c, by the way. And the shortcut is that when you have to bump up the exponent to a fraction, when you divide by that fraction, again, it's creating this complex fraction. So notice, I'll show you the math to get rid of it, and I'll probably show it to you once or twice more. But then pretty soon you'll just start seeing me go straight to my shortcut. So when you have x to the 3/2 divided by 3/2, to get rid of that 3/2 in the bottom, you would multiply by the reciprocal, 2/3 and 2/3. So here, my 3 times 2 would be 6, right here, so I'm looking here. 3 times 2 is 6 on the top of that fraction, and then 3 times 2 is 6 on the bottom of that fraction. So the denominator is essentially equal to 1. So I would kind of cross those off and say that's 1. And then in the numerator, I essentially have 2x to the 3/2 over 3 plus c. And so my shortcut from now on is when I do bump up this exponent, instead of rewriting it as x to the 1/2 and then changing it to this, I'm going to rewrite it as x to the 3/2. And I'm going to write divided by 3, but instead of dividing by the 2 after that, I'm going to multiply by 2. So you guys will see me go straight from this step at the integral to this step, where I divide by 3 and multiply by 2. And that is my final answer. Again, maybe they would write it like that. Maybe they would put it back into radical form. If they did, it would just be the square root of x cubed, 2 times the square root of x cubed over 3 plus c. So, again, as long as you're familiar with both of those forms and how we get from one to the other, that's perfect. Alright, here's some more that we have to rewrite. So, again, if you're feeling gutsy, go ahead and pause the video, see how many of you guys, see how many of these you can do on your own before I help you. So, on this first one, if I rewrite it, this would be the integral of 2 times y to the 1/3 minus 4 times y to the 1/4 dy. And again, notice that we're changing up the variables here, but that's okay because they're telling us that our important variable is y. So it's okay that we have y's in here as long as our important variable is y. As soon as these are different variables, we would encounter a problem. So the integral of 2y to the 1/3, we have this 2 out front tagging along for the ride because it's a constant multiple. If you bump up the exponent by 1, 1/3 plus 1 is 4/3. And then again, divide by 4, but then I'm going to actually multiply by 3. There's that little shortcut I was talking to you guys about just on the last slide. For this next one, the 4 is a constant multiple. Y to the 1/4 bumps up to 5/4. And then divide by 5, multiply by 4. Since we're dividing by 5/4, instead I'm going to multiply by the reciprocal. And then plus c. If I want to simplify a little bit, on this first one, 2 times 3 is 6. Multiplying the 2 here and the 3 here, that's 6. 6 over 4 is 3/2. So this is 3/2 times the cubed root of y to the 4th power. Again, free response versus multiple choice, it's okay to leave your answer unsimplified for free response. For the second one, minus, if I multiply the 4s, I have 16 over 5, which does not simplify, so that's 16 fifths. And then I have the fourth root of y to the 5th power plus c. For this middle one, if I rewrite it, I have the integral of x to the negative 1/2 minus x to the 2/3 dx. We're back to x's again, and my important variable is dx. The integral of x to the negative 1/2. If I add 1 to negative 1/2, I get a positive 1/2. So this is x to the 1/2 over 1/2. So over 1 times 2. For again, that shortcut. And then minus x to the 2/3. If I add 1 to 2/3, that would be 5/3 over 5 times 3. And then plus c. If I rewrite this, I have 2 times the square root of x minus 3/5 times the cubed root of x to the 5th power plus c. And last but not least, this is kind of a weird one. I can rewrite it first. This is x to the pi plus pi to the 1/2 dx. Now, for this first one, the integral of x to the pi, if I bump up pi by 1, but I don't want to like round it as a decimal, I want to keep it as actually like the correct answer, then I would have to just literally write it as x to the pi plus 1 over pi plus 1, my new exponent, plus, and then I know this kind of looks a little funky since we're not used to dealing with pi's too often, but pi is just a constant. So pi to the 1/2 is just another constant, and the integral of a constant is just that constant times x plus c. So I'd probably just leave my answer like that. You're probably not going to see one like that on the AP test anyway. If you did, the only other thing I think that they might do is convert that back into square root of pi instead of leaving it as pi to the 1/2. But other than that, they'd probably leave it like that. Alright, here are our last 3 problems for today. So on these ones, they give us a little bit of a hint, like maybe it's too difficult to take the integral as you see it now. So instead, why don't we simplify it and then we can take the integral. So for example, on the first one, they want us to actually multiply it out and then take the integral. So if I multiply out 2x minus 3 squared, I get 4x squared minus 6x would give me minus 12x, and then plus 9 dx. If I take the integral of that, that's 4x cubed over 3 minus 12x squared over 2 plus 9x plus c. And the only thing I can really do is simplify that middle term. So I have 4/3 x cubed minus 6x squared plus 9x plus c. For this middle one, there's a trick number 2. The trick is to split it into individual fractions and then integrate. So what it means by that is take x squared over x to the 4th, for example. Then divide 3x by x to the 4th. Then divide 1 by x to the 4th and write them as 3 separate fractions and then integrate them after you've simplified. So for example, we have x squared over x to the 4th plus 3x over x to the 4th plus 1 over x to the 4th dx. If I simplify each of these fractions, the first one gives me 1 over x squared, because I have 2 of my x's on the top and 2 of my x's on the bottom going away. Another way to think of this is the quotient rule for exponents. If I have x to the 2nd power over x to the 4th power, I can subtract the exponents. So x to the 2nd power minus 4 would be x to the negative 2. So I'm just going to write it like that, x to the negative 2. The middle one gives me 3 times x to the negative 3, because one of the x's on top and one of the x's on the bottom would go away, so we'd be left with x cubed on the bottom, and if you bring it up, that's x to the negative 3. But again, you could have gotten that from properties of exponents, just subtracting them. And then the last one is plus x to the negative 4 dx. So now that we have all of these written in power rule form, I can actually take the integral of all of them. The first one, if you bump up the exponent by 1, a negative 2 becomes a negative 1 divided by negative 1. The second one, 3x to the negative 3 becomes 3x to the negative 2 divided by negative 2. The next one, x to the negative 4 becomes x to the negative 3 divided by negative 3. And then plus c. If I wanted to rewrite this a little bit, the first one I could write as 1 over negative x. The second one I could put negative 3 over 2x squared. And the last one I could write as negative 1 over 3x cubed plus c. Again, that's probably the way that you would see it written on the AP test, on a free response section. On a multiple choice question, for example. Alright, and then this last one wants us to multiply and then split into separate fractions and simplify and then integrate. So kind of just a bunch of stuff rolled up into one. If I multiply in the top, I get 6x squared. Then outside would give me 4x and inside would give me negative 15x. So that gives me negative 11x. And then last would be minus 10. All over x to the 1/2. If I split these up into separate fractions, so kind of like what we did earlier where we do 6x squared over x to the 1/2. The first one would be 6x squared over x to the 1/2, which simplifies to 6x to the 3/2. And again, I just got that from subtracting the exponents. 2 minus 1/2 is 3/2. For the second one, if I have x to the 1, 1 minus 1/2 is 1/2. So this middle term would be negative 11x to the 1/2. And then for the last one, I would have minus 10 over x to the 1/2. So essentially, I would just bring that up top. That would be minus 10x to the negative 1/2. I'll write that a little neater. Alright, and again, we're still taking the integral of this. Dx is our important variable. Put some parentheses around that. And now it's time for us to actually take the integral. So the integral of x to the 3/2. This is 6 times x to the, if I bump it up by 1, that would be 5/2. Over 5 and then times 2 for the reciprocal. For the middle one, minus 11. If I bump up 1/2, x to the 1/2 by 1, that would be x to the 3/2 over 3 times 2 for halves. And the last one, minus 10, if I bump up negative 1/2 by 1, that would be 10x to the positive 1/2 over 1, and then the half would be times 2. I don't have room for it, but my plus c, I'll write it on the next step. Don't forget about plus c at this step, though. Alright, so let me simplify. 6 and 2 make 12. 12 over 5 does not simplify, so this is 12/5. And then I'm just going to keep it as x to the 5/2 for right now. But I'm hoping you know how to convert that back into radical form. I could have written this as the square root of x to the 5th power. For the second one, if I multiply 11 and 2, I get 22 over 3. Again, does not simplify, so this is minus 22 over 3. X to the 3/2. And the last one, if I multiply, I get 10 and 2 to be 20. So this is minus 20 x to the 1/2. 1/2. And then plus c. And that is about as simple, other than putting those back into radical form, that's about as simple as that one will get. So we're going to stop here for today. We'll pick up with the integrals of trig functions tomorrow.